Hi, I'm Robert J. Lang. I'm a physicist and origami artist, and today I've been challenged to explain origami in 5 levels. If you know a little origami, you might think it's nothing more than simple toys like cranes or cootie catchers. But origami is much more than that. Out of the vast cloud of origami possibilities, I've chosen 5 different levels that illustrate the diversity of this art. Do you know what origami is?
Is that where you fold paper to make different animals like those?
Yes, in fact it is. Have you ever done any origami before?
Nope.
Would you like to give it a try?
Sure. Okay,
so we'll do some, but I want to tell you a little bit about origami. Most origami follows 2, I'll call them customs, almost like rules. It's usually from a square, and the other is it's usually folded with no cuts. So these guys are folded from an uncut square.
That's awesome.
So you ready?
Yep.
Okay, we're going to start with a model that every Japanese person learns in kindergarten. It's called a crane, traditional origami design. It's over 400 years old. So people have been doing what we're about to do for 400 years.
Wow.
Let's fold it in half from corner to corner, unfold it, and then we'll fold it in half the other direction, also corner to corner. But we're going to lift it up, and we're going to hold the fold with both hands. We're going to bring these corners together, making a little pocket. And then, this is the trickiest part of this whole design. So you're going to put your finger underneath the top layer, and we're going to try to make that layer fold right along the edge. Now you see how the sides kind of want to come in as you're doing that?
Yeah.
It's called a petal fold. It's a part of a lot of origami designs, but it's key to the crane. Now we're ready for the magic. We're going to hold it in between thumb and forefinger, reach inside, grab the skinny point that's between the 2 layers, which are the wings, and I'm going to slide it out so it pokes out at an angle. We'll take the 2 wings, we spread them out to the side, and you have made your first origami crane.
Wow.
Now, this is a traditional Japanese design, but there are origami designs that have been around so long, we're not entirely sure where they originated. We're going to learn how to fold a cootie catcher.
Okay,
so we'll start with the white side up, and we're going to fold it in half from corner to corner, and we'll unfold. And now we're going to fold all 4 corners to the crossing point in the center. We'll fold it in half like a book. On the folded side, we'll take one of the folded corners. I'm going to fold it up through all layers. There's a pocket in the middle. We're going to spread the pocket and bring all 4 corners together. Where you have original corners of the square, we're going to just pop those out. This is one of the most satisfying moments, I think.
Yeah.
Because it suddenly changes shape.
I have seen these before. My friends use these.
Yeah, but there's something else we can do with this model. If we set it down and push on the middle, then pop it inside out so that 3 flaps come up and 1 stays down. And then it's called talking crow because here's a little crow's beak and mouth.
Wow.
There's thousands of other origami designs, but these are some of the first people learn, and this was in fact one of the first origami designs I learned some 50 years ago.
Wow.
So what do you think of that? What do you think of origami?
I think that the people that make them are talented. It's hard. Seeing the stuff that we've made here, I'd bet that they could do rocket ships, just so much that you can do with them.
Thanks for coming.
Thanks for having me.
A lot of origami is animals, birds, and things. There's also a branch of origami that is, it's more abstract or geometric, called tessellations. Tessellations, like most origami, are folded from a single sheet of paper, but they make patterns, like whether it's woven patterns or like that or woven patterns like this. If you hold them up to the light, you can see patterns. The thing that makes them cool is they're sort of like tilings. It looks like you could put this together by cutting little pieces of paper and sliding them together. But there's still one sheet.
They weren't cut?
There's no cuts in these, just folding. We can build these up from smaller building blocks of folds. Learn how to fold little pieces and put them together in the same way that a tiling like this looks like it's built up of little pieces. Can you make a fold that starts at the dot, that doesn't run all the way across the paper?
How about like that?
Each of these folds is peaked like a mountain. And we call these mountain folds.
Okay.
But if I made it the other way, then it's shaped this way, and I'm going to call it a valley fold. In all of origami, there's just mountains and valleys.
So all the folds are like reversible?
So they're all reversible. And it turns out that in every origami shape that folds flat, it's going to be either 3 mountains and a valley, or if we're looking at the backside, 3 valleys and a mountain.
Oh.
They always differ by 2. That's a rule of all flat origami, no matter how many folds come together at a point. And I'm going to show you a building block of tessellations. It's called a twist because that center square, as I unfold it,
Twist.
it twists, it rotates. If I had another twist in the same sheet of paper, I could make these folds connect with that, and these folds connect with that. And if I had another one up here, I could make all 3. And if I had a square array and all the folds lined up, I could make bigger and bigger arrays like these, because these are just very large twists. In this case, it's an octagon rather than a square, but they're arranged in rows and columns. And let's just try going along. All right, there is our tessellation with squares and hexagons. So you've now designed and folded your first origami tessellation. And perhaps you can see how just using this idea of building up tiles and small building blocks, you could make tessellations as big and complex as you want.
That was cool.
Yeah. So what do you think now of origami and tessellations?
Origami, I think, is the folding of paper to make anything in general, from 3D things to like flat things. And I think origami is about turning simple things into complex things. And it's all about patterns.
That is a great definition. So here's a dragonfly, and he's got 6 legs, 4 wings. Here's a spider with 8 legs, ants with legs. And these, just like the crane, are folded from a single uncut square.
What?
To figure out how to do that, we need to learn a little bit about what makes a point. So let's come back to the crane. You can probably tell that the corners of this square ended up as points.
Yes.
Right? That's a corner. 4 corners of the square, 4 points. How would you make 1 point out of this sheet of paper?
I'm thinking of like a paper airplane.
Yeah,
Type.
exactly. Actually, you've discovered something pretty neat because you made your point not from a corner. So you've already discovered one of the key insights. Any flap, any point, leg of the ant, takes up a circular region of paper. Here's our boundary. To make your point from an edge, you use that much paper. And the shape, it's almost a circle. If we take the crane, we'll see if the circles are visible in the crane pattern. And here's the crane pattern. And here's a boundary of the wing.
Okay.
And here's the other wing. The crane has 4 circles, but actually there's a little bit of a surprise, because what about this? There's a 5th circle, which is like that. But does the crane have a 5th flap in it? Let's refold it and put the wings up. Well, yes, there is. There's another point.
Oh, okay.
And that point is the 5th circle of our crane.
Okay.
And to do that, we use a new technique called circle packing, in which all of the long features of the design are represented by circles. So each leg becomes a circle, each wing becomes a circle, and things that can be big and thick, like the head or the abdomen, can be points in the middle. Now we have the basic idea of how to design a pattern. We just count the number of legs we want. We want a spider if it's got, let's say, 8 legs. It's also got an abdomen, that's another point, and it's got a head, so maybe that's 10 points. If we find an arrangement of 10 circles, we should be able to fold that into a spider. So in this book, Origami Insects 2, it's one of my books and has some patterns. And this is one of them for a flying ladybug. And in fact, it is exactly this flying ladybug. We've got the crease pattern here in the circles, and you might now be able to see which circles end up as which parts, knowing that the largest features, like the wings, are going to be the largest circles. Smaller points will be smaller circles. So any thoughts? Which might be?
Well, the legs and the antenna would probably have to be these smaller ones in the middle.
Yeah, that's right.
Oh, this looks like the back because it's a bunch of circles. all the way down, like here.
Mm-hmm, exactly.
And
And then the wings.
you've got 4 big wings, which you can see on the ends there, and then I guess the head.
You got it. So you are ready to design origami.
Awesome.
Origami artists all around the world now use ideas like this to design not just insects, but animals and birds and all sorts of things that are, I think, unbelievably complex and realistic, but most importantly, beautiful.
Wow, that's so impressive. I think I learned how to make one of these paper cranes when I was in 3rd grade, but I guess I never unfolded it to actually see where it was coming from. And so now that it's all broken up into circles, it makes these super complicated, insects and animals and everything seem so much simpler. So that's so cool.
That's
I'm really
pretty
excited about it. Thank you so much for telling me about this.
Whenever there's a part of a spacecraft that is shaped somewhat like paper, meaning it's big and flat, we can use folding mechanisms from origami to make it smaller. Telescopes, solar arrays, they need to be packed into a rocket, go up, but then expand in a very controlled, deterministic way when they get up into space. These are the building blocks of many, many origami deployable shapes. It's called a degree 4 vertex. It's the number of lines. So in this case, we use solid lines for mountain, we use dashed lines for valley. We're going to fold it and use these two to illustrate some important properties of origami mechanisms. It's important in the study of mechanisms to take into account the rigidity. So what we're going to do to help simulate rigidity is to take these rectangles and we're going to fold them over and over so that they just become stiff and rigid.
Okay.
So this is what's called a single degree of freedom mechanism. You have 1 degree of freedom. I can choose this fold. And then if these are perfectly rigid, every other fold angle is fully determined. One of the key behaviors here is that with the smaller angles up here, the 2 folds that are the same parity and the folds that are of opposite parity move at about the same rate. But with this, as we're getting closer to 90 degrees, we find they move at very different rates. And then at the end of the motion, the opposite happens. This one is almost folded, but this one goes through a much larger motion. So the relative speeds differ. So when we start sticking together vertices like this, if they're individually single degree of freedom, then we can make very large mechanisms that open and close, but with just 1 degree of freedom. So these are examples of a pattern called the Miura Ori. When you stretch them out, they're pretty big.
Okay.
And they fold flat. And a pattern almost exactly like this was used for a solar array for a Japanese mission that flew in 1995.
So then you fly it up compactly. And then once you get up there, there's some sort of motorized mechanism, but you only need it on 1 fold.
Yeah, so typically what the mechanism will run from corner to corner, diagonally 2 opposite corners.
Okay.
Because then you can stretch it out that way. Notice some differences between the one you have and the one I have, and how this one sort of opens out almost evenly, but this one opens out more one way and then the other.
Yeah. What sort of angle would you want so that they open at the same rate?
Infinitesimally small.
Okay.
So sadly, the only way to get them at exactly the same rate is when these are microscopic slivers.
Sure,
and then that's not useful. And it's exactly the difference between the motions of these 2 vertices. So these angles are closer to right angles, and the closer you get to a right angle, the more asymmetry there is between the 2 directions of motion. And then the other difference is how efficiently they pack. So these started at about the same size, but when they're flat, notice that yours is much more compact. So if I were making a solar array, I'd say, oh, I want that one. But if I say, well, I want them to open at the same rate, then I want this one. So
it's kind of a trade-off.
There's an engineering trade-off to get them both to work. And there's another place that shows up in deployable structures in a very cool structure. This is a folded tube. It sort of pops out like this, but it has this neat property that if you twist it quickly, it changes color. There's a Mars rover application where they need a sleeve that protects a drill, and as the drill goes down, the sleeve is going to collapse, and they're using a pattern very much like this.
Interesting.
There are many open mathematical questions, and so room for mathematicians like yourself to have a big impact on the world of origami and mechanisms. And even though those studies are mathematically interesting, they're going to also have real-world applications in space, solar arrays, drills, telescopes, and more. Any questions or thoughts about this?
If you want to like send something to space, it probably makes sense to do it compactly. So if you have something that you can fold up and then unfold at just like one of the folds, that's going to be probably the easiest way to get something up there and expand it to what it needs to be.
I'm Tom Hull. I'm a math professor, mathematician. I've been doing origami since I was 8 years old and studying the mathematics of origami ever since grad school, at least.
The first thing I want to show you is origami in the real world.
right.
This is the origami lamp. It comes shipped flat, but it folds. Clip holds it together. The lamp has LEDs on the inside, so when we power it up, we get light, we have a lampshade, and we get the base.
Why does origami lend itself to, say, this type of application?
Origami applications have in common is that at some stage, the thing is flat. And so whenever you need to either start from a flat state and then take it to a 3D state, or conversely, for deployables like space, you want to have it in a fully folded flat state, but then take it to a 3D state, or possibly an unfolded flat state. Whenever a flat state is involved, origami is a really effective way of making the transition between those states.
Another aspect of origami and origami mechanisms that has lent itself to many different uses is the fact that it's scalable. When you have an origami crease pattern, like the mirror ori used in solar panel deployment, the type of motion that you see happening here will happen whether this is on a piece of paper that's small like this, or on a larger scale, or even on a smaller scale. Engineers, in particular robotics engineers, are turning to origami for designing mechanisms that will either be really big or really, really small. This looks like the most promising way of getting nanorobotics to work.
This is another real-world application, but this particular implementation is used to make a wheel for a rover.
Cool, so this is something that can actually get really, really tiny, but then get big and fat and roll.
New problems arise when we try to make origami out of things other than paper, but also new opportunities. An example here, which is a kind of a variant of the Miura Ori. It's got a three-dimensional structure. If I stretch it one way, it expands the other. But because it has these S-bends in the pattern, if you squeeze it, it doesn't go all the way flat. This is a epoxy impregnated aramid fiber. And so if I put this fold pattern into it and then compress it, and then put a skin on the top and bottom, this becomes incredibly lightweight, but incredibly strong. Another origami challenge that comes up with these patterns is if we're going to make an aircraft out of this thing, we're going to need hundreds of yards of folded origami. We're not going to do it by hand. And this might be the new frontier in origami engineering, which is the design of machines that can fold patterns that have applications.
So you're talking about a machine that is actually folding it into this, not just making the creases, but actually folding it.
So what goes in is sheet, and what comes out is this, or something this wide.
That's cool, What do you see as kind of like the next big breakthrough? Is there anything out there on the horizon that you're just like, oh wow, this is really exciting?
It's something we've talked about a little bit, that with all the richness of behavior of origami from a flat sheet, it seems like there ought to be an equally rich world of things that don't start flat, but are still made from flat sheets of paper.
So like a cone.
Bistable properties, and you can combine them together with copies of themselves to make cellular structures. They're astonishingly stiff and rigid, useful for mechanics.
The thing that I think I'm the most excited about comes from math mainly. When I look at origami, when I look at all these applications or just all these different origami folds, I see structure. Math is really about patterns. The patterns that we see in origami are reflecting some kind of mathematical structure. And we don't quite know yet what all of that structure is. And if we can tie a mathematical structure that's already well studied to something we see happening in origami, then we can use the math tools right away to help solve the engineering problems and the origami problems. And the fact that there's so many applications to this is really making people excited who are working in the area. I'm really excited to see what happens with that in the next 5 years or so.